Or what happens if one or both of the marginal benefit curves are upward sloping? In that case, it's possible that the intersection between the marginal benefit curves is a minimum rather than a maximum. And so, inframarginal economics allows us to deal with these sorts of problems. The question is it worth the effort? And we can think about this, I guess, in two ways. One is to look at the empirical evidence on the marginal benefit curves. So, do these marginal benefit curves look like the sort of textbook curves in the earlier figures? Here's an empirically estimated curve from Horn et al. So you can see that at very low levels of river flow, this is for the Goulburn River in Victoria, the marginal benefits are essentially zero. Then you've sort of got this jagged upward sloping segment, and then beyond a certain point the marginal benefits are zero again. And so these empirically derived curves look different to these sort of textbook curves that I was showing earlier. And so ideally you want an analytical framework that's capable of dealing with these sorts of possibilities. The other motivation is to, or the other way of thinking about it is to say, well, what are the implications of the sort of marginal framework? If you're equating the marginal benefits across all ecosystems, then the implication is it's going to be efficient to water all ecosystems. You know, there are thousands of wetlands in the Murray-Darling basins. We really believe that it's going to be efficient to water all of those wetlands. Probably not, and so we want a model that's capable of dealing with these sorts of corner solutions. It doesn't require all ecosystems to be watered. So Goddard et al. Developed such a framework. It's a dynamic programming model with stochastic rainfall. They're allocating water between two ecosystems and storage. Each ecosystem has a water requirement, and if it receives that water requirement, it returns to full health, and if it doesn't, over time, over a period of about 5 years, it declines in health before it suffers sort of irreversible damage. And so they set up a situation where there's sufficient water to keep both ecosystems alive in the short run. But it turns out to be efficient to allow one ecosystem to suffer irreversible damage in return for, I guess, keeping more water in storage and reducing the probability of the other ecosystem suffering irreversible damage. And so you sort of get the potential for these sort of corner solutions. I guess the way I think about it is this is just one possibility, like the marginal solution, and that the job of developing, I guess, a more general framework for dealing with these problems still remains. And the way I've sort of gone about it, and there are presumably other ways of doing it, is to apply inframarginal economics. And it looks at sort of using non-classical mathematical programming techniques to solve problems that might have corner solutions. The applications go back as far as Coase in 1946, and the term was first used by Buchanan in 1962. A lot of the applications recently have looked at specialization in the context of international trade, and this program uses a similar approach to Cheng et al. So they have a Ricardian trade model with increasing returns, which are notionally caused by learning costs, and they also have exogenous comparative advantage. And the problem's similar. What they're looking at is the allocation of labour to produce two different goods, and so the model can decide to either produce both goods, and so you have autarky, or they can choose to specialise and produce one good and buy in the other good. And so the approach is fairly similar. So let's look at the model. The model basically is similar to the problem earlier. You're allocating water between two ecosystems to maximise returns, subject to two simple constraints, a non-negativity constraint and a sort of water availability constraint. I use a quadratic environmental production functions with interaction terms. So that means that it's watering ecosystem B has the potential to increase or decrease the output of ecosystem A. And so it's trying to bring in the sort of coordination problems that people talk about when they're looking at these sort of management issues, and it could be a result of return flows or something like that. So in this model there are sort of three potential configurations, to use the jargon. You can water both ecosystems, or you can water ecosystem A only or ecosystem B only. And the task is then to sort of find the conditions under which these conditions apply. So what parameter values, what combination of parameter values do you end up watering both ecosystems or only watering one ecosystem. And so there are a number of ways of doing this. I think the way I've taken this is the most intuitive to me, at least. I'm just going to summarize it because it's not very difficult, but it is messy. And so basically, I use the Kuntaka maximization and minimization problems to find the parameter subspace for an interior stationary point, and for the corners being either local maximum or local minimum. And then looked at the second order conditions to see whether the problem was concave or convex. And this information sort of allowed me to sort of identify sort of 4 different problem types. And so this is I guess the total returns associated with these different sort of allocations of water. And you can have a concave. If it's concave and you've got an interior stationary point, then you know that's going to be your local maximum, global maximum. Here it's convex, and you've got an interior stationary point that's going to be a minimum, and the maximum is going to be one of these corners, in this case the corner with the highest value, which is C, and so it's sufficient to allocate all of your water to ecosystem A and no water to ecosystem B if your problem looks like this. You can also get a corner solution where the problem's concave, and if this is a local maximum, then this will be a global maximum as well. And you can also get a situation like this, where your problem is convex, and you have a local minimum that will be your, the opposite corner will then be your global maximum. And so these are the 4 sort of possible types of solutions that can apply here. So from this you can sort of determine the parameter subspace and the solutions for these different configurations. The results are too sort of long and messy to show, but my paper's here, so you can collect a copy afterwards, and on page 13 it's got all of the expressions for this. Perhaps the easiest way to examine the results then is to do it visually and to look at the... so what I did was I just made up some parameters, and I'm adjusting one parameter at a time and holding the other parameters constant and looking at the effect of adjusting that parameter on the efficient amount of water to allocate to ecosystem A. So here's a case where you have we're adjusting the quadratic term, so this is the environmental production function for ecosystem A, and so it's sort of pushing the marginal benefit curve for ecosystem A out. At very low values of A2, you end up allocating most of your water to ecosystem B. As you increase A2, you end up allocating more and more water to ecosystem A, until you move from an interior solution here to a corner solution where you're allocating all of your water to ecosystem A. Now in this case, the marginal benefit curve associated with ecosystem B is downward sloping, but if it's upward sloping, which it could be, you can get something that looks very different. Something like this, where you start off at a corner where you're allocating all your water to ecosystem B, and then you just sort of jump discontinuously to a situation where you're allocating all of your water to ecosystem A. There's also interaction terms in the model. At very low levels of the sort of interaction term, you end up with a corner solution. All of the water is allocated to ecosystem A in this case. Then as you increase, you move to an interior solution, and you end up getting, as you increase A3, getting a more and more balanced allocation of water. Here's the price term. I'll skip over that. This shows the effect of increasing water availability on the efficient allocation. Initially, at very low levels of water availability, you're allocating all of the water to ecosystem A, and then at this point here, you move to an interior solution where you're allocating additional water between the wetlands or ecosystems. Again, the previous one was drawn for a marginal benefit curve for ecosystem B that's downward sloping. If it happens to be upward sloping, you can get something that looks very different and some sort of potentially counterintuitive results. So here, you're initially allocating all your water to ecosystem A. As you increase water availability more, you move to this interior solution, and an increase in water availability reduces the efficient amount of water allocated to ecosystem A within sort of this range here. And that's because the marginal benefit curve associated with B is upward sloping, so as you sort of shift it out and increase the amount of water available, the benefits at the margin of water in ecosystem B increase, and eventually you end up with a corner where you're only watering ecosystem B. So, what does all this mean? I think some of the main findings are, these corner solutions are certainly possible. and they're possible even when both of the environmental production functions are sort of well behaved, when they're concave and differentiable. And, so in this case, you're more likely to get the corner solutions if the interaction term is smaller, leads to a less balanced allocation of water, or if there's less water available in general. Corner solutions are assured if both of the environmental production functions are convex, and the empirically derived environmental production function from Horn et al. Does obviously have convexities in it, and so if one is convex and one is concave, it becomes an empirical issue. Depends on the magnitudes. So I think the consequence of this is, where you have these corner solutions, you shouldn't necessarily expect sort of smooth and continuous responses. You can get sort of discontinuous jumps and things like that. Another implication is that the interaction terms make a difference as well. This sort of theory is likely to be widely applicable. There's similar research looking at the abatement of air pollutants, and so the issue there is, do you use resources to abate all types of air pollution, or do you specialise in a sense and just focus on abating some types of air pollution? You can also think of applications in other environmental economics applications or agricultural economics applications where you're looking at technology, or at work we were talking about labour markets, and the decision as to how much time you allocate to different jobs is sort of characterised by corner solutions. And if you're looking at, say, whether to take on a ongoing or permanent position of it, you've got sort of the problem's not really differentiable, and so this sort of inframarginal approach is likely to be the way to go there. Back to water, some areas for further research. I think looking at dynamics and uncertainty, and including the ability to carry over water, so you're introducing a marginal user cost into the problem, expanding it to look at more ecosystems, and I guess developing more realism, so more realistic environmental production functions with thresholds and things like that. I've done a little bit of work in that area, and also using empirical data and sort of building the model around these sort of empirically estimated functional forms and things like that, and parameterizing it using empirical data. Any questions?
Yeah.